Cold atomic clock. Last October, the high-profile Mengtian experimental module was successfully launched, carrying the world's first space cold atomic clock group. Its accuracy is astonishing, and it can control the error within 1 second over hundreds of millions of years, successfully breaking the world record. How does it actually work? How is there a connection between time and positioning accuracy? One Mengtian space cold atomic clock group is the most accurate in the world. Nowadays, missile guidance rarely bypasses one thing: satellite positioning. According to academician Sun Jiadong, the chief designer of the Beidou project, the Beidou system cannot be built without an atomic clock. The core principle of the Beidou system positioning is to use multiple satellites to form a network and calculate the distance, obtained by multiplying the signal reception time difference by the speed of electromagnetic wave light, to determine the position of an object on Earth. The accuracy of this algorithm mainly depends on the timing accuracy and the degree of time alignment between satellites. The space atomic clock is known as the heart of navigation satellites, which directly determines the accuracy of navigation and positioning. It can provide a time-frequency reference signal with ultra-high stability for the navigation system, better determine the distance between each other, and directly determine the positioning, speed measurement, and timing accuracy of the navigation system. Whether the accuracy of the navigation system can reach the meter level, decimeter level, or centimeter level depends largely on the performance of the space atomic clock. As the second experimental module of the Tiangong space station, the Mengtian experimental module needs to be composed of 8 experimental cabinets. As the most complex experiment cabinet in the space station, the high-precision time-frequency experiment cabinet has the world's first high-precision time-frequency system consisting of an active hydrogen atomic clock, a cold atomic rubidium clock, and a cold atomic light clock. It is the first high-precision time-frequency system in space. It can control the error within 1 second in 5 billion years. The entire space high-precision time-frequency system consists of a hydrogen clock, a rubidium clock, and a strontium clock. It was developed by the 203 Institute of the Second Institute of Aerospace Science and Industry Group, the Shanghai Institute of Optics and Mechanics of the Chinese Academy of Sciences, and the Wuhan Institute of Physics and Mathematics of the Chinese Academy of Sciences, and is jointly fixed in 2 refrigerator-sized frameworks. The hydrogen clock in the atomic clock group is an active type of hydrogen atomic clock, with an accuracy of millions of years and an error of 1 second. Similar products have been widely used in satellites launched in China as reference objects for calibration. The rubidium clock is a type of cold atomic fountain clock that uses lasers to cool atoms and then uses microwave excitation to count the energy level transitions of rubidium atoms, with an accuracy of 30 million years and an error of 1 second. The most accurate one is the strontium clock, which is also the first light clock in China to be launched into the sky. It counts the energy level transitions of strontium atoms excited by visible light, with an accuracy of up to billions of years and an error of up to billions of years. Different types of cold atomic clock are combined to form a cold atomic clock group. The cold atomic clock group can realize the conversion and comparison between different frequencies, thus improving the stability and reliability of the overall system. After being launched into space, these 3 high and cold clocks can work independently and compare readings with each other, thus measuring time with unprecedented accuracy, even surpassing the most advanced single cold atomic clock on the ground. 2. How does the cold atomic clock time? As a more accurate timing method, the birth of the atomic clock cannot be separated from the rapid development of the nuclear physics in the 1940s. Atoms are the most fundamental units that make up elements and the smallest particles in chemical changes. When an atom transitions from an energy state to a lower energy state, it releases electromagnetic waves, known as resonance frequencies. The characteristic frequency of electromagnetic wave of the same kind of atom is certain, which can be used as a metronome to maintain highly accurate time. The atomic clock is a metronome that generates time pulses by keeping the characteristic frequency of electromagnetic waves synchronized with atoms. The oscillator generates microwave or optical signals, which interact with the atomic medium through a precision-adjustable multiplier, microwave/optical frequency link, to detect the energy state changes after the atomic medium transition, lock the oscillator, and output the standard frequency signal. This is the most basic part of the atomic clock, which is called the atomic frequency standard. With the timer functions such as frequency counting and integration, the whole atomic clock is constructed. After discovering the phenomenon of atomic resonance, physicists began to try to define its vibration results as a standard unit of measurement of time. For example, the resonance frequency of cesium-133 at -273 degrees Celsius is 91926317770 times per second, approximately 9.1 billion times, which is also the current definition of second by the International Conference on Metrology, CGPM. The atomic clock relies on counting to measure the resonance frequency of atoms, and reverses it to achieve accurate timing. Its advantage is that it does not contain radioactivity and is not affected by the relativistic effect. It has the characteristics of low drift, high stability, radiation resistance, small size, light weight, low power consumption, etc., which makes it useful in space. It is called the space atomic clock when it is launched into space to work. The one based on microwave excitation is called a fountain clock, and the one excited by light is called a light clock. The use of cold atoms for timing is because each atom is close to a stationary state, which facilitates the confinement of atoms in a specific space and facilitates human use of vibrational timing. Such atoms are cold as a result rather than a cause. This is why the General Conference on Weights and Measures strictly defines that the cesium atom must be at -273 degrees, the static atom eliminates the interference of motion, and its resonance frequency output will be more stable and easier to be captured by the instrument compared with the more hot and faster moving atoms. This requires special methods to slow down the atoms, resulting in a decrease in temperature, reaching the defined low temperature of -273 degrees. 3. How to make the environment the coldest. The secret of accurate timing of space cold atomic clock is high and cold. On the one hand, it benefits from the micro-G environment in space, and on the other hand, it is because of the cold of the clock itself. Although we cannot see atoms or molecules, the atoms or molecules inside are in motion, and the motion generates heat, which is called a hot atom. Cold atom technology is the use of lasers to reduce the temperature of atoms from room temperature to near absolute zero. Measuring these almost stationary atoms will result in more accurate results. The biggest difficulty in manufacturing a cold atomic clock is to reduce the target atomic speed to near zero. For different research purposes, scientists need to create an environment as close to absolute zero as possible, so that atoms can have a stable state in the coldest environment. This needs to start from the definition of heat energy. The root of making atoms cool is to slow down the atoms by some way. When the speed drops to near zero, the temperature of the system will actually be closer to absolute zero. For this problem, Stephen Chu, a Chinese scientist, proposed the method of laser cooling and trapping atoms, which greatly promoted the development of cold atomic physics, and won the Nobel Prize in 1997. Atoms are composed of atomic nuclei and electrons moving around them. For a certain atom, a stable nucleus requires a huge amount of energy to explode, making it difficult to emit energy for exchange. However, its electrons are prone to interacting with foreign photons. When an electron transitions from a low orbit to a high orbit, it needs to absorb the corresponding energy. When a photon of a specific frequency is absorbed by an atom, according to the conservation of momentum, this will lead to a change in the rate of the atom. Based on this effect, scientists designed a device to incident laser light from 6 directions, adjusting the frequency of the laser to a suitable value for the target atom, ensuring that photons are absorbed. The purpose of this design is that no matter which direction the atom moves in, it will always absorb incoming photons. These atoms appear to be in a sticky syrup formed by photons at a specific frequency, and their rate of motion in all directions will continue to decrease until they are almost stationary, thereby reducing the thermal energy of the entire system. This has become the international standard means of constructing the extremely low temperature environment of the cold atomic clock. With the development of laser cooling atomic technology, the precision of time measurement has been further improved by the cold atomic clock made of laser-cooled atoms, which is developing at a rate of almost an order of magnitude every decade. For ultra-high precision time service assists in the development of multiple fields. Standing tall and looking far, the same applies to satellites. The current spaceborne clocks need to constantly align with the ground cold atomic clock to obtain more accurate time information, but the relatively long distance between the satellite and the ground, as well as the existence of the atmosphere and ionosphere, will lead to fluctuations in the synchronization process. If a precise time service system is established in the inter-satellite link itself, it can serve as the time service center in space, transmitting ultra-high precision time information based on the spatial time coordinate system to other satellites without interference. Through the joint calibration of the Mengtian experimental module, a time-frequency network system in a space coordinate system can be formed, which greatly improves both the timing accuracy in space and the navigation accuracy facing the ground, from meter-level accuracy to centimeter-level accuracy. At the same time, it can also effectively support many basic scientific research, such as demonstrating Einstein's general relativity, more accurately measuring physical constant and the distance between distant galaxies, monitoring the gravitational wave phenomenon, looking for evidence of dark matter and dark energy, exploring gravitational redshift in the universe, observing the merger of distant galaxies, etc., creating better conditions for China's subsequent astrophysical research. Conclusion. Many satellites under China's space exploration plan are millions of kilometers away from each other, but they need to sense the laser signal sent by each other on the millimeter scale, which requires highly accurate time alignment capability. Now, China has the best timing system in space, which will support its research in multiple fields in space. There is no doubt that the cold atomic clock group in the Mengtian experimental module will give new imagination to the exploration of the universe.